Hello, friends. This is Jim with Science Talk. I thought I would do an interesting video for you guys. A little while ago, I did a video about introductory to statistics, looking at hypothesis testing and so forth. So if you have not seen that video, please check it out. In this video, I want to kind of introduce you to the idea of regression, linear regression, and explain to you, some of the things to look at when you see a regression line reported to you in a scientific paper, and what it means when you see things like R squared equals this, R equals that, and so forth. So I thought I kind of pre-drew these in the interest of time, because using this here, I'm not very adept at it. And as you can see, it's a little difficult to draw curved things here. Anyway, I don't know if it's visible. You might want to zoom in on the screen here, but I have a bunch of blue dots here on each of these little graphs, and I have a second prepared screen. The blue dots are supposed to represent data points. And the idea of linear regression, or curvilinear regression, I'll talk about that later on, is to using specific calculation means, statistical approaches, using least squares approach, is we try to find the best fit line or the best fit curve through the data point. So now if I look at this first one here, again, you might want to zoom in to see these blue dots, which I'm indicating with this X here, or this plus sign. Kind of a buckshot. They're like all over the place. So these lines here are very possible regression lines through here. You might notice that this one here is almost horizontal. It's basically would be a slope of 0, flat line. No relationship between the dependent variable, usually placed on the vertical axis, and the independent variable placed on the horizontal axis. If I were to do an R-square calculation on this here, I would have a very poor result. I would probably have a result very close to 0, which means that you can throw this out, it ain't worth squat. Okay, it's just terrible data. Come over to number 2. Again, I got these little these dots here, right? Boom, boom, boom. All these little dots here, and you could fit a line like so, indicated here in this, I guess, fuchsia color. And this is not a bad regression line. I mean, if I was to do an R-squared calculation, I might get something of the order of about, say, 0.75 or something like that. It's not too bad. This would be a reasonable line going through this data point. Now, I would create a model, and the model might be something on the order of, let me change my color here. The typical model would be Y, we call this hat, a little caret over it, and this would equal, say, B sub 0. That's supposed to be a 0, really. Use your imagination. B sub 0, it's a lot harder to use this than you would think. B sub 0 plus, say, B sub 1 x. Okay, x would be my independent variable. So in other words, this is a predictive value. B sub 0 would be my intercept. So if I had, say, extended this line to intersect the vertical axis, that would be my y-intercept. That's represented by B sub 0. In fact, let me sort of do that for here, just so you can. Okay. So let's see, that would be where it intersects. That might be where it intersects there, and likewise there. Okay, so that would be the intercept there. So let's go back to that color there. So that would be this parameter here. B1 is the coefficient for the slope. Okay, coefficient for the slope. Remember from high school algebra, y equals mx plus b. M is the slope, x is your independent variable, and b was your y-intercept. Okay. So after I do my statistical calculation and so on, I come up with a model. Y hat, we call it y hat with the caret over, y hat equals, say, 20 plus 2.7 times x. Okay, so all right, so what would be the predicted value for y when x is this? Okay, so you've got the intercept, you've got the slope, you plug in the x value, you calculate it, you get a predicted value. The predicted value is what falls on the line itself. Now, I could get a predicted value for, say, this x value here, and then compare it with the actual observation. So this x value from here gives me this y value as a response. This is the actual y observed value. The difference between the actual value and the predicted value is called error. As you can see, different points will have different errors. And that's the whole point of doing a least squares analysis, is to you taking into account all these different errors to try and find your best line that fits the data point. This is what modeling is about. We collect data and we create models. It can be something as simple as linear regression or something as complex as climate modeling. But we collect the data, we develop the models, and then we say, okay, let's input some values and see what the predictions are. Coming to graph number 3 here. I tried to draw this, but basically the idea was to have all the blue dots here fall precisely on the regression line. When you have a situation like this, R² equals 1. That means it's a perfect fit. All the data points lies exactly on the regression line. Number 4 here is very similar to number 2, except that there's a tighter clustering of the data around the regression line, except for I have a point here and a point here. So what do we do with those guys? Now, you could run the regression model to include those points, and you would probably get a regression line that looks different with a lower R². But you can also look at this and using statistical calculations to justify, you can remove these as outliers. And then rerun the regression model, and you get a very good fit here with a very high R² value. Okay, so that brings me to this idea. You've heard me mention R². Okay, I'm going to erase that because that looks like crap. Okay, so let's try that again. And that's about as good as I'm going to get that. So R². R² has values between 0 and 1. Right? It has values between those two. The value of 0 means it's shit. Okay, be blunt about it. There is absolutely no fit of the data to the line. That's basically situation number 1 here. This is basically shit. It's complete crap. Don't bother with it. Okay? A value of 1 is where all the data points lies exactly precisely on the line. Something I tried to demonstrate here in situation 3. If someone reports to you an R² of 1, eyebrows go up. Very, very rarely, if ever, you get data points exactly on the line. You'll get something like this, okay, or like this. Now, this R square might be something on the order of, say, 0.75. Okay? This is probably like 0.02 or something like that, probably 0. And this would be 1. That's what I was trying to show. Because I got some little bumps here, probably 0.99998 or something like that. But you get the idea. This one here is a little tighter, so I might have an R square of something like, say, 0.9. This looks pretty good. Might be 94. Okay. Now, what does an R squared what does the R squared value mean? Okay, I already told you the two extremes, 0 and 1. Another way of looking at it is saying, like in this case here, R squared equals 0.75. That means 75% of the variation in the response of the dependent variable can be explained by the independent variable. Let me state that again. 75% of the variation in the response of the dependent variable can be explained by the independent variable. In this case here, 94% of the variation is explained by variation as seen in the responses of the dependent variable is explained by the independent variable. Now, oftentimes, okay, you might add a second independent variable. So now I'm going to give them subscripts, x2, x1. And now, and let's say that this was my situation here with just the one independent variable. I add the second independent variable, and now I get this situation here. So now we can say, these two independent variables explain 94% of the variation in the response of the dependent variable. When you get something like this, you have a really excellent model. We usually like to shoot for an R squared of about 0.85 minimally. So this would be okay. This is better. Now, that's one. So R squared measures how well the data points themselves fit the fitted line or the fitted curve. How well does it conform to what we just calculated? That's what the R square tells you. And it tells you in terms of how much percentage of the variation can be explained. There is another measure, and that measure is called R. Now, R has values ranging from -1 to +1. That's the range of values for R. Now, R is not simply the square root of R squared. I used to have my statistics students make this mistake all the time. They would calculate the R square, and I asked them to calculate R, and they would just take the square root of R square. And if you have a situation, as I'm going to show you in the next screen, you have a wrong answer. What R itself shows you, that value, it shows the correlation between the variables. So let's just, again, keep it simple, and let's just say I am just considering this model alone, just the one variable. A value of -1 tells us that the variables, dependent and independent variable, are strongly negatively correlated. +1 means they're strongly positively correlated. If you have an R squared of 0, that means there ain't no correlation at all. That's like this situation here. Okay. The value of r, I should say, excuse me, the sign of r using a one independent variable system typically corresponds to the sign of the coefficient for the independent variable. So I could have an r of minus 0.92 and have a very high r square. Possible. Let me give you an example. Let's look at this guy here. Let's look at number 5. Okay. Number 5, we see, well, again, we see our blue dots here, and we see a slope. It has negative slope. Now, my r square here might be something, again, like a 0.78 or what have you. But I could have a r of minus 0.92, as I just said. You know, they're strongly negatively correlated. Just like going back to here, there's a strong positive correlation. A good positive correlation. Very good, very strong positive correlation. This one I might have an R value of, say, 0.7a, 0.82, what have you. This one I might have an R value of 0.9, 0.92, what have you. You have to get the data points and calculate it out. So R squared tells you how well the data points fits the model. It tells you the variation explained by the independent variables in the response of the dependent variable. R tells you how strongly correlated the variables are to each other. As I said, if I look at my regression line here, my B1 parameter will be positive. Positive slope increases to the right. Same thing here, same thing here. Over here, my slope would be negative. So I would have, so B1 would be minus, less than 0, and my R will be also negative, strong negative correlation. So those are the things you want to look for when you look at regressions. However, not everything is always going to be nicely explained by a straight line. You could have a situation, and let's look at number 6 here. You got all these data points kind of. Now I could try and put a line like here. I could try something like that. Okay. If I were to do that, my R square might be in the 0.6 something realm. Okay. But using what we call curvilinear analyses, curvilinear being you can account for exponential functions, trigonometric functions, polynomial functions, logistic functions, logarithmic functions, and so forth. You can then come up with models that fit that. If I was to do that here, okay, the diffusion line kind of indicates that we have an exponential function going on here. And this R square might give me a better R square. This will probably, in this case here, this will probably give me like a low 0.7 or something like that. Like this one actually might be like high upper 0.5s. But the point is, this gives me a better R square. So that tells me that that function would be better to use, an exponential one, than a straight line one to try to model that situation. Likewise here, I have all these points here. If I was to put a line through here, a linear, I would get something like that. This is not going to be a great R squared. This is probably going to be like a 0.3. But if I do a curvilinear, we see very nicely a cubic function. And this is going to have it's probably like a 0.885 R squared. This is much better. This is what's actually going on. What about over here? Again, I got all these points here. We fit this curve here. If I was to try to put a straight line through here, I might get something like this. Trying to draw it straight. You can see it's just, this is not going to be good. But this fuchsia line will fit it much better. In fact, we call this a logistic growth. A logistic curve has two components to it. It has, and let me put a blue, I don't want blue, that's too close in color to that. Let me put red. I'm just going to put a line right there. Okay. There's two components to it. This first component is exponential, like this. The second component on the other side of this blob I just drew in, this is a logarithmic curve portion of it. So a logistic curve contains an exponential beginning. The first part of the function follows an exponential function. The second part follows a logarithmic function. Where the changeover is, we call that an inflection point. So if you've taken calculus, you know the inflection point is where the concavity of the curve changes from concave up to concave down or vice versa, provided there's continuity through the point. Where do we see logistic curves? Population. Let's say I have a species that shows up into an area. It's ripe for the picking. You know, there's no competition. There's a niche to be filled. So what happens? There's plenty of space. So territory is not an issue. There's plenty of food and water. The population grows exponentially. As it grows exponentially, the resources, territory, food, water, starts to become limiting. We start seeing a slowdown in the growth until it reaches some horizontal asymptotic level, plateaus out, in other words. Asymptote is a line that a function approaches but does not intersect. That is very true for oblique and vertical asymptotes. Horizontal asymptotes can be intersected, but it's more of a function how the function itself behaves as we go to infinity. Don't want to turn this into a calculus class, but anyway. But basically, we're reaching a plateau, so we get a horizontal asymptotic value. Now, it's going to oscillate around it. You know, a little bit of overpopulation, corrective measures, so the population sinks down below. Okay, so there's more available resources, the more reproduction takes place, overshoots a bit, and just repeats this oscillation around it. Those are negative feedback loops, corrective measures. Right? You've heard me talk about that in other videos. What this plateauing represents, or the oscillation around that asymptotic value, what that represents is called the carrying capacity. Carrying capacity is the number of individuals of a species that an ecosystem can support based on available resources. So usually when you trying to determine, trying to model the population for a species, what have you, it's going to typically follow what we call the logistic growth pattern. You're going to have an initial burst of exponential growth activity. It slows down until it plateaus out at some value which typically pertains to the carrying capacity. So we would have n, the number of individuals on the vertical axis, and we'd have time, t, on the horizontal axis. Carrying capacity, the number of individuals of a species in the ecosystem can support based on available resources, food, water, space, typically being the big three. So the whole idea is that when you see papers that report to you a regression model, or they give you a graph, a whole bunch of dots, and here's a line here, and also lots of times they may even draw little error flags. So if I was to do an enlarged version of it, here's your data point, you might have an error flag like this, plus or minus kind of stuff. So you might see that reported as well. And then, and usually with that, with in the error bar, the line should pass within it. So you would expect to see the line come in something like, say, that, or maybe it's down here. You wouldn't want to see it up here. Then you might have an outlier, and you can get rid of it. So usually each individual point will have their own error bar. So some might be taller, some might be shorter. But typically the regression curve, line of curve, will go in between the error flags. So you can have where a straight line does nicely, or other cases you might need to use a curvilinear function. This is exponential, this is cubic, this is logistic. You could have others that are trigonometric, let's say, if it's a sine wave, or a log function that just does that. Okay, you can see log function does that as you go down to infinity. There's none of that kick it out as an exponential component of. So the logistic, as I said before, is a combination of an exponential aspect and a logarithmic aspect. So you can get things like that. And of course, just as before, I can have one, two, or more independent variables. And usually, as you add more and more variables, the R-square should increase. You can then look for the R value, the correlation of the dependent to each of the to all. You can do an R value of the dependent variable compared to each independent variable separately or or all together to show that. So you might say, well, it's better correlated to this variable, not so much that variable. You can do that kind of stuff. So I wanted to bring this little video to you to help you understand how to look at regression models, linear or curvilinear or otherwise, so that you know what's meant by the R-square and by the R. So I hope you found this informative, and thank you for your time. Please share. Hey folks, just a reminder to please subscribe and click the bell so you know when I drop a video. Please share my videos. Please tell others of my channel and of the work that I do. I also hope that you will consider becoming a patron at patreon.com/Science Talk with Jim Massa, where from time to time I upload videos there exclusively for my patron subscribers. Details in the description box below.